So now that we've constructed the dual space, which is just simply the set of all structure-preserving maps between our vector space and its underlying field, the real numbers, the elements of which are dual vectors, sometimes also called covectors or one-forms. These dual vectors are just linear maps from the vector space into the real numbers. So now it's a perfectly natural question to ask, what's the dual space of the dual space, which we might call V star star. So we can work this out by simply going through the exact same construction as we did before. We simply ask, what is the set of all linear maps between the dual space and the underlying field? Remember, the dual space and the vector space have to be over the same field for all of this to make sense. So an element of this double dual space is just going to be a linear map from the dual space into the real numbers. So now this is where things can get a little bit abstract and confusing, and I'm not really going to want to dwell too much on the details of this. I'm just basically going to tell you that the double dual space is, in fact, in a very natural sense, what we call isomorphic to the actual initial vector space. And now we can only understand this in the case where the vector space is a finite dimensional, otherwise it doesn't work. But this isomorphism essentially means that we can make no distinction between the elements of V and V double dual. They are, in a sense, the same, because we can construct an isomorphism, which just means an invertible map, meaning that we can go freely between V and V double dual, and the underlying structures, the underlying operations are the same. So this is just a bit of abstract mathematical nonsense. If you want to really dig into the details of this, it's going to be beyond what we're going to need. But what we need to take away from it is that there is a very natural sense in which we can think of vectors, so the elements of V, as being kind of the same thing as double dual vectors, which just means that vectors are simply linear maps from the dual space into the real numbers. So now this bracket notation we're going to see becomes much more useful for us. So to see this, I'm going to just drop the bracket notation for a second and consider a vector in the space, which I'll just remind you is the same thing as the double dual space. It can take a dual vector, and I'm going to switch to a function-y style notation just for a moment. I've been using this bracket notation. We can switch freely between them. It's just whichever makes sense in context. So a vector can act on a dual vector to give us a real number, but what this isomorphism kind of tells us is that we can do the operation the other way around. That dual vector can eat the vector to also give us a real number. And so that's why we see this bracket notation being the most useful, in that since a vector is either going to be fed into a dual vector or the other way around, it makes sense to just pair them up naturally like this, which is why it's sometimes called the natural pairing. The natural pairing of these vector and a dual vector. And this is always just going to give a real number. So from now on, we're going to write dual vectors as linear maps waiting for a vector, and just as equally we can think of vectors as being linear maps waiting for a dual vector input. So that was just very quick, very rough and hand-wavy. The actual details of this are a lot more complicated, but what we need to take away from it is that there is a very natural sense in which we can think of these double dual vectors as being essentially the same thing as actual vectors. And so going forward, we can think of these dual vectors as linear maps waiting to eat a vector, and vectors as linear maps waiting to eat dual vector.